The beginning of nuclear power, the pressurized water reactor, and the design of 3 Mile Island, by Brian Rivera, Duke 495, Thomas Edison State College. So the topics that will be covered during this presentation: the origin of nuclear power, development of nuclear fission, the neutron, the discovery of fission, the atomic bomb, America's increased research of the atomic bomb, the Manhattan Project. Development of nuclear power plants, Admiral Hyman G. Rickover, the pressurized water reactor and systems involved, and advantages and disadvantages of the pressurized water reactor, and the 3 Mile Island design and layout. The origin of nuclear power. The nuclear power industry has come a long way from being first found as a type of ionizing radiation and evolving into the vast power plants that are seen all over the world today. As with any power industry, the beginnings of nuclear energy was first harnessed in labs by scientists trying to figure out what exactly was causing the radiation they were finding to be emitted. Although we now use the fission reaction to produce electrical power everywhere, the early findings of these scientists were initially used for nuclear weapons. The evolution of the fission reaction and how it could be used was the main frame of the development of nuclear weapons, leading to such events as the Manhattan Project and the development of the Soviet bomb. These developments would then lead to the power industry, what would become some of the greatest breakthroughs of all time. Development of nuclear fission. The development of nuclear fission began with the findings of Wilhelm Röntgen. In 1895, Röntgen discovered ionizing radiation by passing an electric current through an evacuated glass tube, producing continuous X-rays. Although this was just the very beginning, this finding led the way for other scientists to explain this phenomenon that he discovered. This phenomenon that he discovered was eventually named radioactivity by Pierre and Marie Curie. The Curies are two of the well-known physicists who were the foundation of main discoveries when it came to the origin of nuclear power. In 1898, they isolated polonium and radium from pitchblende. Pitchblende is a black pitchy form of the crystalline uranium oxide mineral uranite and is one of the primary mineral ores of uranium. The substance also was used in the findings of the element uranium by German chemist Martin Klaproth in 1789. The results of their findings led to them earning the Nobel Peace Prize in 1906 in physics. Based on these earliest discoveries, more breakthroughs such as the finding of radioisotopes and eventually the discovery of the neutron would aid in the eventual discovery of fission. This would begin the eventual attempt to harness this reaction, and also in the attempt to find a self-sustaining chain reaction. The neutron. Discovery of the neutron led to the discovery of fission, based on the fact that when neutrons were fired at uranium, it resulted in a reaction that caused elements that were much lighter than uranium to form. This was first initially found by physicist Enrico Fermi in 1934. Fermi conducted experiments in Rome that showed neutrons could split into many kinds of atoms. In 1938, two German scientists, Otto Hahn and Fritz Strassmann, fired neutrons from a source containing the elements radium and beryllium into uranium, resulting in the finding of lighter elements such as barium and the leftover materials. Although the findings of the elements were crucial in the development of nuclear energy, it did not make sense when the elements were added up, and it was found that they did not match the mass of uranium. This was discovered by Lise Meitner. Meitner would use Einstein's theory of E equals mc squared to show that the mass loss changed energy. This proof fission occurred and confirmed Einstein's work. The discovery of Lise Meitner would then lead to the discovery of fission. The first self-sustaining chain reaction was discovered by Fermi in 1942. A self-sustaining chain reaction occurs when fission happens, emitting neutrons that would then go on to react with other uranium nuclei and cause more fissions to happen. This would, of course, require a lot of uranium-235, which has to be enriched from uranium-238. This is due to the fact that only 0.7% of natural uranium consists of uranium-235, while the other 93.3% is uranium-238, although they both have the same chemical properties, which create research of the scientists involved in finding how to create a self-sustained chain reaction had no intentions in using it for war, beginning of World War II changed the purpose of the aforementioned reaction. Most of the research following the findings of Fermi was used not to create energy to be used in a power system, to be used in a defense weapon during a time of war. This began the research in order to create an atomic bomb that could be used whenever needed. The first major research that was done towards the creation of an atomic bomb was done by the British, beginning with the studies of Rudolf Peierls and Otto Frisch, two physicists who fled to Britain during the Second World War. These two physicists predicted that an amount of about 5 kilograms of pure uranium-235 can make a very powerful atomic bomb equivalent to several thousand tons of dynamite. They also figured out how to detonate this bomb, how to produce uranium-235, and the radiation effects the bomb would cause. This paper that was written by them was known as the Frisch-Peierls Memorandum and stimulated a considerable response in Britain. This resulted in the development of a research development team in Britain, who would at first set the standard for atomic bomb development around the world. This would all change, however, once Japan attacked Pearl Harbor on December 7, 1941. America's increased research. The attack on the United States of America led to the immediate increase in the efforts of the USA to develop an atomic bomb. This project would famously become known as the Manhattan Project. At first, the project was led by a few American scientists who, with the help of the British, were working on different enrichment processes in order to create the enriched uranium that would be needed in order to build the bomb. However, in June of 1942, the U.S. Army took over process development, engineering design, procurement of materials, and site selection for pilot plants for 4 methods of making fissionable material, as well as the production of heavy water. After a few years of development in the main laboratory located in Los Alamos, New Mexico, the first atomic bomb was exploded at 5:30 a.m. on July 16, 1945, at a site on the Alamogordo Air Base. It was detonated on top of a steel tower surrounded by scientific equipment, with remote monitoring taking place in the bunkers 10,000 yards away. This was the first successful detonation of the atomic bomb, leading to 2 more, the first being on Hiroshima and the second on Nagasaki, Japan, in August of 1945. The first bomb contained uranium-235, while the second bomb contained plutonium-239. This event ended the Second World War, but in turn started the nuclear age all over the world. Here is a picture of the mushroom cloud that was a result of detonating the first atomic bomb in 1945. Here's a picture of the 2 bombs that were dropped on Hiroshima and Nagasaki, Japan. The 2 bombs were named Little Boy and Fat Man. At the conclusion of World War II, it was time to turn efforts of using the self-sustained chain reaction from using it to develop weapons of mass destruction to a peaceful and beneficial application. Although weapons development never really stopped, a new focus on harnessing the great atomic power now dramatically demonstrated it for making steam electricity. From the development of the atomic bomb came a vast improvement in the technologies that were used to not only enrich the uranium, but also in the way in which the self-sustained chain reaction could be caused to occur. In 1951, the first nuclear reactor to produce electricity was the experimental breeder reactor in Idaho. Although this was just a small amount of electricity, it was considered to be a giant step for the development of the commercial nuclear power. As nuclear reactors began to develop for commercial use, the Atomic Energy Commission, or AEC, was developed in order to supervise nuclear power plants in the USA. This commission consisted of 5 members who managed these programs until the Atomic Energy Act was passed in 1954. The Atomic Energy Act redefined the atomic energy program by ending the government monopoly on technical data and making the growth of private commercial nuclear industry an urgent national goal. The Atomic Energy Act would change the face of the development of nuclear power in the United States, which would soon be at the head of nuclear power in the world. Although the AEC still managed the commercial development of nuclear power, the focus of the Commission had shifted with the passing of the Atomic Energy Act. The AEC was assigned 3 major roles: to continue its weapons program, to promote the private use of atomic energy for peaceful applications, and protect public health and safety from the hazards of commercial nuclear power. However, it seemed as if there was an eager push to develop commercial power plants instead. Not only was this due to the energy demands of the nation, but also due to the fact that at the same time the commercial nuclear power was beginning to develop in the USA, Other countries began to excel in nuclear power as well. Because of this, I feared that the United States would fall behind, and the nuclear power race was high. Take in mind that this was right in the middle of the Cold War, where if at any point in time it seemed that the USA was falling behind the USSR, there was sure to be a problem with the public viewpoint. However, over the next 10 to 15 years, the USA would make great strides along the development of nuclear power with the help of Admiral Hyman G. Rickover. Here's a picture of Admiral Hyman G. Rickover, otherwise known as the father of the nuclear navy. The greatest effort that was taking place during the development of the nuclear reactor was due to Admiral Rickover, head of naval reactors. Admiral Rickover developed a pressurized water reactor for naval, or particularly the pressurized water reactor used enriched uranium oxide fuel and was moderated and cooled by ordinary light water. The Mark I prototype naval reactor started up in March 1953 in Idaho, and the first nuclear-powered submarine was launched in 1954. The development of this type of reactor only opened the doors for commercial plants to not only use its design, but to also develop it even further to meet the needs of a commercial power plant or to produce enough electrical power to supply electricity to thousands of people. All over the world, different types of reactors began to be designed, including some in Canada and the Soviet Union. Although these designs resulted in the production of nuclear energy, only one has stood out from the rest and is most widely used all over the world: the pressurized water reactor. Commonly known and used type of reactor is the pressurized water reactor, or PWR. This type of reactor has over 230 in use for power generation and several hundred more employed for naval propulsion. In the 1950s, this design of reactor was initially for submarines, but was developed into a larger design in order to be able to supply power in the commercial field. There are many different types of designs that have been developed over the years of this reactor, but they all use the same principles. PWR is to use water as both coolant for the reactor and as a moderator. A moderator will slow down the speed of neutrons in order to control the rate at which power is achieved by the reactor. The components of a PWR are also very important to its operation and are the keys to safe reactor operation. The design of a PWR is distinguished by having a primary cooling circuit which flows through the core of the reactor at high pressure and a secondary circuit in which steam is generated to drive the turbine. The amount of loops each reactor contains is varying on the purpose or the type of PWR that's being used. The loop is considered to be on the primary side of the reactor, which in some cases will contain a coolant pump and a steam generator, although this is not always the case. PWR also includes anywhere from 150 to 200 fuel assemblies, which are arranged vertically in the core. Reactors have evolved over the years into becoming some of the top-of-the-line nuclear reactors. The reactor vessel of a PWR contains several different components such as the core barrel, the reactor core, and the upper internals package. The vessel itself contains inlet-outlet nozzles that allow the entry of water into the core in order to provide cooling, and there is one inlet and outlet nozzle per coolant loop. The core barrel slides down inside the reactor vessel and houses the fuel, while the upper internals package sits on top of the fuel and contains the guide columns in order to guide the control rods. The reactor coolant flows from the steam generator. Inside the steam generator, hot reactor coolant flows inside many U-tubes. The secondary coolant flows around the outside of the tubes where it picks up heat from the primary coolant. When the feed water absorbs sufficient heat, it starts to boil and form steam. There are many different variations of a steam generator depending on the design that's being used. However, all of them pipe the steam to the main turbine. Shown at the right is a Babcock and Wilcox 1-3 steam generator. This design was used in the 3 Mile Island design. The primary coolant that transfers heat to the steam generator is then routed to the suction reactor coolant pump. These pumps will then direct coolant back to the reactor vessel. Pressurized water reactors also contain a pressurizer. The sole purpose of a pressurizer is to help maintain pressure in the reactor itself and to prevent boiling from occurring in the core. The secondary side of the PWR contains all the auxiliary systems that are used in conjunction with the primary side. The main secondary systems are the main steam system and the condensate feed water system. Since the primary and secondary systems are physically separated from each other, the secondary system will contain little or no radioactive material. Other systems can be installed as well that will aid in the removal of decay heat from the reactor. Decay heat is the heat that is still generated from the fission process even after the reactor is shut down. Core cooling system is installed as a protective feature. There are two main purposes of the emergency core cooling system. The first is to provide core cooling to minimize fuel damage following a loss of coolant accident. This is accomplished by the injection of a large amount of cool, borated water into the reactor coolant system. The second is to provide extra neutron poisons to ensure the reactor remains shut down following the cooldown associated with the main steam line rupture, which is accomplished by the use of the same borated water source. The combination of these systems, along with safe operation, are what make a pressurized water reactor the most useful type of reactor that is used today. Although the pressurized water reactor is one of the most commonly used reactors all over the world, there are still some advantages and disadvantages when it comes to the design and operation of them. Some of the major advantages of the PWR is that they are very easy to operate due to the stability of the reactor, and there is an ability to initiate a scram that will place the reactor in a safe condition if power is removed. The major advantage of a PWR is the fact that the coolant water in the primary circuit never comes into contact with the secondary circuit, which will result in a lower radiation level in the turbine. With the lower radiation levels on the secondary side, this will also make the exposure that is felt by personnel working on the equipment lower as well. Disadvantages to operating the pressurized water reactor. One disadvantage is that the water must be highly pressurized in order to keep it from boiling whenever operating at higher temperature. A few other disadvantages when it comes to the fuel is that the fuel that is used must be enriched to a certain percentage, and if there ever was a primary rupture, the water would easily flash the steam. This could cause even more extreme problems, such as electrical equipment grounds or burns to personnel if the steam escaped to the engine room. Also, the high pumping requirements in operating at higher pressures increase pressure vessel containment requirements. We will now shift our discussion to 3 Mile Island. The history and development of 3 Mile Island. 3 Mile Island Nuclear Station is located in Middletown, Pennsylvania, and contains 2 reactor units, Unit 1 and Unit 2. Construction for TMI began in 1968 with the first unit, while the second unit's construction began shortly in 1970. Both of TMI's units are pressurized water reactors that were designed by Babcock & Wilcox, one of the major power companies at that point in time, and built by Gilbert Industries. However, TMI was not the first nuclear power plant that was developed in the United States. As previously stated, nuclear power had been in development for quite some time before TMI was designed, built, and online for commercial use in 1974. Since the implementation into commercial power, TMI has been a competitive component of the nuclear power industry. At the time of construction of both of the units, TMI was operated by Metropolitan Edison, otherwise referred to in many documents as MET-ED. Nuclear power itself had very little resistance to operation during the first initial times of TMI-1 coming online. There was very little public worry about nuclear power based on the fact there had hardly any knowledge of nuclear energy due to its relatively new implementation into the energy production industry. Nuclear power plants were being built all over the country, and there had not been any major accidents at the time. However, this would all change in 1978 when a series of equipment failures, inappropriate procedures, human errors, and ignorance would change the nation's nuclear power industry for years to come. Here's a diagram of a TMI unit. On the left, you have an auxiliary building, in the middle is the reactor building, and on the right is the turbine building. We will now go into discussion of each of these buildings. As stated before, TMI was home to 2 nuclear power plants, TMI-1 and TMI-2, only one of which is operating today. Both plants were operational. They had a capacity of up to 1,700 megawatts and were jointly owned by Pennsylvania Electric Company, Jersey Central Power and Light, and MET-ED. The primary fuel source for TMI-2 was uranium. At TMI-2, the reactor core held 100 tons of uranium in the form of uranium oxide. This uranium oxide was molten into pellets that were stacked on top of each other inside fuel rods, which are about 12 feet long and made of zircaloy, which is more commonly known as cladding. This so-called cladding was used due to the fact that it would allow the transfer of heat to be completed easily, allowing most neutrons to pass through. TMI-2's reactor contained 36,816 fuel rods, with 208 rods in each of 177 fuel rods. A A fuel assembly contains the fuel rods and space for the cooling water to flow between the rods, as well as any other tubes that contain instruments to measure temperature inside the core. For TMI-2, there are 52 tubes that contain instruments and 69 with control rods. On the left is a picture of the fuel pellets that are contained in the fuel rods. On the right, you can see workers transmitting a fuel assembly down into the reactor core. The reactor vessel itself was around 40 feet high and had a steel wall over 40 inches in thickness. Inside of the reactor vessel are the aforementioned control rods in the actual reactor core. Around the vessel were two separated concrete and steel shields. These would reduce the amount of radiation, and they measured right around 9.5 feet thick. The entire enclosure was also placed inside a containment building that was made of concrete that stood 193 feet high and almost 4 feet thick. On the primary side of the reactor, borated water was used based on the fact that boron is a neutron absorber and will aid in the ability of the operator to control reactivity during operation. The concentration of boron early in core life is around 2,000 parts per million and is reduced greatly as the core is operated for a longer period of time due to the fact that boron itself is very corrosive. Ion exchangers are used to remove it. As mentioned earlier, this pressurized water reactor keeps the plant pressure high to prevent the water from boiling inside the core due to the fact that the water is also kept at a very high temperature. In order to control this pressure, a bubble is maintained within the pressurizer by using heater elements. TMI-2 had a pressurizer that was 42 feet tall and held right around 800 cubic feet of water with 700 cubic feet of steam on top of the pressurizer to maintain the pressure right around 2,155 pounds. With the pressurizer, the plant also had two steam generators that were designed by Babcock and Wilcox. These steam generators were one-seer type that were 92 feet long with the bottom below the core inlets. They were designed this way in order for the primary side to develop natural circulation in the event that the coolant pumps were not running, or if there was only a limited amount of cooling water on the secondary side. The purpose of the steam generator was to remove the heat that was on the primary side and use it to create steam on the secondary, thus resulting in driving the turbines that were used to create electrical power. Building were two other buildings that housed the auxiliary equipment as well as the turbines. Inside the turbine building were the turbines and associated equipment that are needed in order for its operation. By using the steam from the steam generators, electricity was generated. This is what used to power the distribution systems in the area. Once the steam is driven to the turbine, it enters a condenser where the steam is condensed and sent back to the steam generator through the condensating feed pumps. There is an auxiliary feed water pump as well in this building that provide water to the steam generator in the event that the normal feed lineup is not available. These pumps would receive water from a condensate storage tank in order to fill the steam generators if need be. The other building was referred to as the auxiliary building and contained a radioactive waste system and the high-pressure injection pumps that were used in the immersive core cooling system. The radioactive waste system would receive water from some pumps from the reactor or containment building and would store this water if needed to. Also, a few safety components and features that were implemented in order to prevent damage to the core in certain situations. The first was the immersive core cooling system that we discussed earlier. This would be used in order to inject water into the reactor core in the event that a major loss of water was incurred. The system uses the high-pressure injection pumps that are housed in the auxiliary building to achieve a flow rate of 1,000 gallons per minute. These pumps will pump borated water into the core from the borated water storage tank. Another safety feature that was used was the safety valves installed on top of the pressurizer. These valves were installed to prevent overpressurization from an overpressure condition that could cause the vessel to rupture. This valve was designed to lift at 2,225 pounds, 100 pounds above the normal operating pressure. This valve would relieve to a relief tank that was designed to collect the radioactive water released if the pilot-operated relief valve were to lift. Also, the plant was designed with an automatic protection feature called a scram. When this scram occurs, power is removed from their mechanism holding the control rods in place, allowing them to fall to the bottom of the core and placed in the reactor itself in a shutdown condition. The control rods for TMI-2 were made of cadmium, which is a strong neutron absorber, which will stop the nuclear chain reaction and will maintain the plant in a shutdown condition along with the borated water. In conclusion, today we have talked about the origin of nuclear power, the pressurized water reactor, and 3 Mile Island. Once again, Again, the topics that we covered were the origin of nuclear power, development of nuclear fission, the neutron, discovery of fission, the atomic bomb, America's increased research of the atomic bomb, the Manhattan Project. We also talked about the development of nuclear power plants, Admiral Hyman G. Rickover, the pressurized water reactor and the systems involved, advantages and disadvantages of the pressurized water reactor, and 3 Mile Island design and layout. Thank you for watching my presentation. I hope you enjoyed it.